In this video, I will explain you quality factor or sharpness of a circuit. Now, in an Lcr circuit, resistance, inductor and capacitor. I am giving an input and input is Em sin omega t is the input, and let's say this is a tuned circuit. Tuned circuit means it is running at the maximum current. Okay, maximum current possible in the circuit. So value of current I is equal to Vm divided by Z in an Lcr circuit. So Z have to be minimum. So what is the condition? So I am going to draw the graph. This would be the graph. Where this is the maximum value of current Im, and that occur at a frequency of natural frequency of the Lcr circuit, which is omega 0 is equal to 1 by root Lc. Now what I am saying is, when we are setting the value of omega as omega 0, when we are setting the value of omega as omega 0, we would get the maximum value of current possible or maximum value or minimum value of impedance possible. Now let's say this is a tuning circuit, and to the tuning circuit there are different voltage coming in. So that is nothing but voltage due to the electromagnetic wave. So for example, one voltage is due to one radio, this is a radio station, this one is a radio station. From a radio station, different frequencies are coming. For example, 93.5, 92.5, 97.5. Now, what I can do is, I can tune the circuit so that I can change the capacitance of this capacitive circuit. So this is an Lcr circuit, right? Now the capacitor would be in this way. What is the value of capacitance? Epsilon 0 A by D. Now the value of capacitance is dependent on the distance in between two capacitive plates. So when the distance is increased, value of capacitor will decrease. Okay. Now when the value of capacitor is decreased, we know what will happen to the natural frequency of this Lcr circuit. That would be 1 by root Lc. So when C value decreases, the natural frequency of this circuit increases. Now see, let's say as of now we have tuned to a radio station of 93.5. So when we have tuned to a radio station means, now at 93.5 Hz this circuit is finding its resonance. Okay, so which means that 1 by root Lc is equal to 93.5. Now the same circuit, if we want to listen to a radio station which is 97.5. Now if I am keeping my circuit at such a value where its resonant frequency is equal to 92.5, then we can't listen to those signals which is sent at 97.5. Now what I have to do is, I have to tune the circuit so that this distance in between these two capacitive plates will increase. When the capacitive plate is increased, now distance increases, the value of capacitance decreases. When C decreases, the natural frequency of the circuit increases, and at a point where the natural frequency become 97.5, then I can listen to those particular station. So this is called as tuning circuit. Okay, so whichever the radio station we need or whichever the TV station we need, we can change the value of C. See here, it is not possible to change the value of resistor because it is fixed. Now inductor also, it is difficult to change the value. The one which is easy to change is the value of capacitor. So changing the value of capacitor is associated with the rotation of the knob. Whenever we are increasing, rotating it rightward and leftward, basically the capacitance decreases or increases, and this we are setting at different natural frequencies where it will find its resonance or delivers the maximum value of current, and that is nothing but the radio station which we want to listen. Now see, now comes the problem that when the radio is being tuned at 97.5, when this is not exactly 97.5, maybe 97.3 or 97.4, at these values have you listened to multiple radio stations at the same time, but when this become 97.5 exactly, then we are only able to listen to those particular station. Now what I am saying is, see, this is 97.5, the one which we want to listen. Now we know that when the frequency is less than this or greater than this, what will happen? The value of current would be decreased and we won't be able to see that voice clearly. But thing is, we still be able to listen to those frequencies where it makes this, see, this is associated with a power, right? What is the power here? That is the maximum power. Maximum power is equal to I0 square R. This is the maximum power of this LCR circuit. I0 is the maximum value of current and R is the resistance. Now why I have multiplied it with resistance? Why I am not doing it with Z? See, we know that at frequency, at resonance, the value of Z would be equal to R. Why? Z is equal to root of XC minus XL the whole square plus R square. So at resonance this would be 0, so only R would be there. This is the maximum value of power. Now we would also be able to listen to all the power in between maximum value and maximum half of the maximum value of power. Now half of the maximum value is nothing but half of this I square, I0 square R divided by 2. So there the value of current would be, so if I am writing it as just multiplying with I square R, then I can say that I at that position will be I0 by root 2. So this is nothing but RMS value of the current. But anyway, in between the half value of the maximum power and the full value of maximum power, all the frequency we would be able to listen through radio. So all these frequency, this represents the PM by 2, half of the maximum power. This is the maximum power. So this frequency is not a problem with us. Now this is a problem, right? See, we are able to listen to wide range of frequencies. So this won't give us the clear picture of the frequency, which the clear picture or the clear voice of the frequency which we have to tune in. So instead of this, now I am going to redraw this. Instead of this, if our curve is in this way, then this would be maximum power and this would be half of maximum, PM divided by 2. See, now only this frequency we have to listen, but here in this case this is the maximum power and this is half of the maximum power, PM by 2. Now all these frequencies initially we have to listen. Maximum power, this is one curve, and maximum power of this curve and half of the maximum power of this curve, and all these frequency we have to listen. So this is omega 0, this one is omega 0, the middle one, the dotted line is omega 0. Now I am going to write omega 1, omega 2, this is this I will make, yeah, omega 1, omega 2, this one I will keep it omega 1, omega 2, omega 3, omega 4. Previously all the frequency, this was the previous curve, all the frequency in between omega 1 and omega 4 we would be able to listen through the audio. So this is not having the voice output with the best clarity. But when we are making the circuit, the same circuit having a curve in this way, see, in between P max and P max by 2 we only have to listen this in between these two frequency, omega 2 and omega 3. So I can say that this circuit is more sharp and it is having better quality because we only have to listen to this much bandwidth. This is called as bandwidth. So this, if this is omega 0 and this distance is delta omega towards Pm by 2 and this is delta omega. So I can say that delta omega plus delta omega will be the net bandwidth. So here the bandwidth is 2 delta omega. Now when the curve is in this way, delta omega would be this and this. See, this would be the 2 delta omega. All this frequency we have to listen. That will give a lot of noise. But here in this case, delta omega, only this one. But here, this much we have to listen. So this is the quality of the circuit. So sharpness of the tuning or quality factor has been defined as operating frequency. This is the operating frequency, natural frequency, omega 0, divided by bandwidth. What is the bandwidth? Delta omega plus delta omega, 2 delta omega. So this is the bandwidth, this is the operating frequency. Now with this circuit, omega 0 divided by 2 delta omega. See, this value is less. This is less, so quality factor would be more. Now with this circuit, see, omega 0 is the same thing, but delta omega, 2 delta omega is higher and quality factor is less. So this equation is very important. Now I will give you an example. Let's say the input voltage is 2. Okay. Now at resonance, you know that the total voltage drop across this circuit will be only due to the resistance. Why? You know, at inductor the voltage would be leading, at capacitor voltage would be lagging, but at resonance VL is equal to VC. So the net voltage drop across these two would be equal and opposite. So that won't be there in the picture. We will only have this voltage drop and that value will be I into R. So basically it is I into Z, but Z value at resonance would be R. So this would be the voltage drop across R. Now, so if the value of the input is 2, now what would be the value of this? If the resonance is 5, this would be 2 into 5, 10. Now if the inductor is, say for example 5, and frequency of the input signal if it is 500, now we know that this value L omega is the XL and that value will be 5 into omega 500. So this is 2500. Okay, that is the value of XL. Now what would be the voltage drop here? If I am just connecting a speaker here, voltage drop here would be VL is equal to I into XL. So I is 2 ampere. Okay, let's say I in the circuit is 2 and voltage is also 2. I into XL is 2500. So this is 5000. So it's such a high amplitude here. I have basically amplified the input, right? I have given a voltage input which was 2 volt and I have given, this 2 volt was sending a current of 2. Now when the same current reaches here, it gives a voltage output of 2500. So it's such a loud and clear voice. So I can also define my quality factor as voltage across L or C. So that would be equal at resonance. This is VL, this is VC. VL and VC would be equal. So that value would be, what is voltage across L or C? I into XL or I into XC. So I am going to take I into XL divided by voltage across R is nothing but I into R. Now I and I will cancel and XL is equal to L omega and R is R itself. Now for omega I am going to substitute as 1 by root LC and this is R. So this L and root L will cancel and that value will be 1 by R will be there, 1 by R into root of L by C. So L and root L will cancel and I will have root L here and this will be root L by root C and R will come here. So this is the quality factor, 1 by R into root of L by C. Now higher the value of inductance, higher self-inductance, higher would be the quality factor, and lower the value of capacitance, higher will be the value of quality factor. Now lower the value of resistance, higher would be quality factor. Now if in question if they are asking how to increase the quality factor, answer is increasing L, decreasing C, decreasing R will give you a higher value of quality factor. Okay, so this is the sharpness or quality factor of an LCR circuit. Okay, thank you.